Okay, so turn to 15-3 in your notes. We're going to talk a little bit about current carrying wires and that they themselves can produce magnetic fields. And so when we talk about fields, in order for two things to interact through a field, they both have to be producing a field of their own. And so we've talked about how a current carrying wire can feel a force, F sub B equals Bill sine theta. And if there's a magnetic force on a current carrying wire that is in that magnetic field, then he himself is producing a magnetic field around the wire. And so that's what we're going to talk about today. So take a look at your notes, 15-3. It says, this is towards the bottom page, it says a long, straight current carrying wire produces a magnetic field. I'll go ahead and highlight that. So a long, straight current carrying wire produces a magnetic field. The strength of the magnetic field is given by the following equation. So another way of saying strength is the magnitude. So let's go ahead and write that down, magnitude. So the magnitude of the magnetic field is given by this equation. So this is my magnetic field, so that is B. That is equal to mu naught. Now that's mu naught is just a constant, which will always be given to you, but mu naught is 4 pi times 10 to the negative 7th Teslas times meters over amps. Then I, of course, is in amps. That's the current in the wire. So B is the field produced by the wire. So this is the field produced by wire. Okay. I is the current in the wire, and B is going to be in Teslas. This is the current in the wire, and that will be in amps. And then over 2 pi r, and r is the distance to some point from the center of the wire. Okay, and that will be in meters. So really quickly, if I just had a wire traveling to the right, and let's say current was flowing like that, if I pick some spot right above the wire, the distance r would be that distance there. Okay, so the distance r is the distance from some random point relative to the wire. So if the wire is just out in space and it's carrying a current, it will produce a magnetic field around itself, and the magnitude, the size of it, is given by this equation. So let's go ahead and write that equation, and I'll go ahead and erase the A and the B right there. So that's the equation that's given right there. Now, just like this equation there, and then the FB equals QVB sine theta, those give magnitudes. That's the size. So I plug in, remember we said that that could be absolute value right there. And so they give me magnitude, they give me size. How do I determine the direction of the force? We use something called the right-hand rule. And let's review that. Our thumb was the velocity or the direction of motion, so velocity or the current. That was our thumb. Our fingers represented the field that in this case, the charged particle was in. That's the field that it's in. Not that it's producing, but that it's in. This is the magnetic field that current carrying wire is in. So that would be my fingers or your fingers. And then the direction of your palm, which is going to cause the force, is the direction of the force. All right. And so that's the connection between direction, direction, the magnetic field direction, and then the force. The right-hand rule is also going to be used for determining the direction here. Now, it's different. There's two right-hand rules. Okay, so there's two versions. The one that we already know is for determining, the one we know is for determining the direction of the force. That's your palm. Okay, the palm represents the force. The other version, you're simply just going to grab the wire and your thumb points in the direction of the current. So we've already had our thumb point in the direction of the current. This should be easy. Okay, so take a look. Here's what's going to happen. All right, what you're going to do is you're going to grab the wire. So let's say current is flowing through this wire like this. Okay, so current's flowing up. You're going to grab the wire with the direction of your thumb. So the thumb points in the direction of current flow. Then you're going to grab the wire. So really there's only two ways to grab wire. Either thumb points that way or your thumb points down, your fingers grab the other way. All right? And so your thumb is going to represent the direction of the current flow, just like it was in the previous right-hand rule. But then here, your fingers, which still represent the magnetic field, are going to grab the wire. Now what's really cool about magnetic fields is they create circular fields around wires. All right, so by me grabbing it, take a look, this person's grabbing the wire like that. It's creating a field that wraps around the wire in such a direction. All right, so let's take a look. Let's say there's a wire carrying current at you. So remember, a dot is representing current carrying at you. So imagine the current's coming towards you out of the screen. All right, so you'd point your thumb out towards you, and then when you go to grab the wire, your fingers would wrap around in a counterclockwise direction. And so if I drew just a dotted line the same distance away from every spot that's right there, all right, if I pick some spot, remember the magnetic field doesn't curve, it's tangent there. So the magnetic field is kind of curving all around like this. Okay, so here's my magnetic field curving, and it's making a counterclockwise, but at different locations it points tangent. And as long as I'm the same distance away, r, all those values can be determined in terms of the magnetic field. The magnetic field at any point at some distance r from the center, so that's from the center, r is equal to mu naught constant times my current in the wire all over 2 pi r. And so what I can do is if I pick some spot that, let's say that's the spot, that distance is my r, the magnetic field points in the direction like that, and so I can determine what the magnetic field is by this current carrying wire. All right, let's take a look at another example. All right, so let's say current is traveling straight up, okay? Your thumb is in the direction of the current. Your fingers will wrap around to represent the field, just like in the previous right-hand rule, but we're determining the direction of the magnetic field here, not the force, okay? So the first right-hand rule determines that. The second determines the direction of your B field, your magnetic field. So the first version tells me the direction of the force. The second direction is B field. And so let's go back to this. So this guy is grabbing the wire. His thumb points up. His fingers are wrapping around the wire in such a fashion like this. And so if I look, you see how there are field lines that are going in this type of direction. Now, as you get further from the wire, because once again, B equals mu naught I all over 2 pi r, because you get further, r is getting bigger. So the r for that guy, that guy, and that guy are all getting bigger and bigger. And since r is getting bigger, then the magnetic field would go down. So the magnetic field at this spot would be lower than this spot. And so we represent that. Remember, with field lines, the further they are apart, the weaker the field. So that's what this is representing. See how these lines are closer together? And then as you get further from the wire, they get bigger. So the next one might even look like that kind of thing, but they're all in that same type of direction. Now, if all of a sudden I flip the direction of the current, then all these things would be the exact same circles. They would just, the arrows would point in the opposite direction. So magnetic fields form circular, a current carrying wire will form circular fields around itself. Okay, so make sure we know that. All right, so let's look at the next page. So flip over and let's take a look at 15.4. And it says determine the magnetic field vector B at a 0.5 centimeters above a long current carrying a wire carrying a current of 10 amps. And so 5 centimeters is my distance away from the wire, and 10 amps is the current that it's carrying. So what I want to do, go ahead and do this too, is let's draw a wire. Let me make this a little thicker. So let's draw a wire like this. And let's say the current is going to the right. So we'll say I is going to the right, hypothetically for this particular case. Okay? And so I'm going to pick some random spot right above here. And so this distance from there to there is 5 centimeters, which we want to be 0.05 meters. So let's go ahead and do this problem together in the packet. All right. And that's my magnetic field, or that's the spot of interest. And so I want to find the magnetic field there. So we're finding B. So B, the magnitude, is equal to mu naught I all over 2 pi r. So I'm going to plug in. Mu naught, remember, is a constant. It's just that 4 pi times 10 to the negative 7th Teslas times meter all over amp. And then I'm going to multiply by my current of 10 amps. And so there's 10 amps. And then I'm going to divide by 2 pi times my radius of 0.05 meters. Okay, and so if I plug that in my calculator, I'll get 4 times 10 to the 1, 2, 3, 4, 5, negative 5. And then take a look. Meter and meter cancels, amps and amps cancel. And so I get 4 times 10 to the negative 5th Tesla. So that's the magnitude of my field. So that's 4 times 10 to the negative 5th Teslas at that spot. Now we got to determine the direction. So here we go. According to my picture, the current is going to the right. So what you would do is you'd put your thumb in the direction of the right, and then you try to go grab the wire. Well, if you think about it, if I'm grabbing the wire with my thumb pointing this way, there's my thumb, my fingers will go underneath the wire. Okay? So my fingers will go underneath the wire, and then as I grab it, they're going to wrap behind and pop out from over here on the top. So if you think about grabbing something horizontal where your thumb's got to point to the right, your fingers will wrap underneath the wire and then they'll curve out on top. And so the magnetic field at that spot in the plane of the wire and that dot is your fingers would curl straight out at you. And so here, my magnetic field would be a dot. Okay, down below the magnetic field, because I'm grabbing the wire down below, my fingers go underneath it. It would actually be an X, saying that the field is going away from me. So imagine that these are forming circles. If I can rotate it, they would be forming a circle. If the wire was kind of going at an angle right there, they'd be forming circles, and at the top it'd be coming out at us, and underneath it'd be going away from us. And so at that spot, we would say out of page. All right, if this was the direction of the wire. Okay, let's try another one. What if the direction of the wire, let's say the current was going up like that? All right, when I go to grab the wire, the current is going up, so my thumb goes up, and then when I go to grab, my fingers would swing back behind the wire, and they would point at me here, and they would be going into the board there. Well, if you think about it, that's the same thing as this. If I rotate it over to make it flat, it would just look like that. All right, so take a look at this. If you need to review it again, go ahead and do so.